Land. Okay, cool. So today we're starting volumes of revolution. So this is like 6.5 part 3 or part 4 or part 17. We've been in this chapter for a long time, okay? This is directly from the textbook. This is called the DISC method, and this is going to be on page 522. This is kind of the middle of page 522. And I went ahead and took screenshots because the pictures kind of make the lesson. If you're not able to see these pictures, you kind of have no idea what we're doing at all. Okay, so the DISC method. So it says we can apply the general method for finding the volume of a solid to a special case. What if the cross sections are circular cylinders or discs? That's all a disc is. It's a short, squatty little cylinder, right? Imagine that I took a cylinder and now I made a disc out of it, right? If a region in a plane is revolved about a line in the plane. So what that's saying is this. I have this function f of x. Can y'all see this picture right here? I have this function f of x. And the region R is cut out by f of x and some line y equals c. Sometimes that's the x-axis, sometimes it's not. Okay. And let's say I took this region R and I started rotating it. Like this. What's it making as it's rotating? It's making a circle. It's making a circle. Yeah, that's how things do. Think of like a rotisserie chicken. Okay, we put a chicken on a spigot and we start like this with it. Well, every time it turns, it rotates in a circle. So the volume or this solid that's created by doing this has circular cross sections. Can you see that? Okay, I went to school and one of my professors, my Cal 2 professor, was actually a German man from Canada. So it was kind of this whole thing. But he talked about a cake that they baked in, I don't remember if they baked this cake in Germany or if they baked it in Canada. I don't know, but it's a foreign cake. And what happened was they would paint this batter on a spigot, and then they would put it in the oven and it would rotate. And every time that the batter baked, they would add another layer of batter. Like that. And so by the end of it, when you cut it, you had this cake that was in rings. Look like a spiral kind of cake. Because every time that it would turn a rotation and bake, they would add more batter. And then they would put it back in, and it would do the same thing, and then they would add to it like that. Well, so that's how they ended up with this big cake. And when you cut a cross-section, you could see like a tree trunk, all the rings in it, right? In my mind, that's kind of what's happening here. They're rotating this function on an axis, and they're forming a solid shape by doing that. Pottery, yeah, exactly. Very much like pottery. Here, the shape is solid. Okay, come back tomorrow and it might not be. But here we've got a solid, so every section is a disc. Okay, it's a little cylinder. The cross section is a circle. That's so helpful because every time our area is area of a circle. We don't have to deal with an equilateral triangle turned on its left side sideways. We don't care. It's always a circle. And so the area of each cross section is always going to be pi r squared. So the only thing that really changes here is r. Your radius is typically going to be the function. So I'm zooming in right here. Radius is typically going to be found by taking the function and subtracting the axis of rotation. So if your axis is on the x-axis, it's just going to be radius as the function because I would do minus 0, right? But if my radius my axis of revolution is moved anywhere else, that's going to play into how deep your radius might be. Yeah? Okay. Okay, so here we have area is pi r squared, where r is the distance from the function to the axis of revolution. One thing that we want to make sure that we do, and we'll see this in a minute, if we have a horizontal axis of revolution, horizontal axis, what that means is we're rotating about something parallel to the x-axis. Something parallel to the x-axis. So anytime they give me, this is going to be about a number y equals a number, Those are parallel to the x-axis. Anytime we're rotating parallel to the x-axis, we're in dx. Because the size of that circle is going to change as x fluctuates, right? Anytime that we're revolving about something parallel to the y-axis. So if they give me x equals a number, that's a vertical axis of rotation. Then my function's not going to change as x changes, but as y changes. So we'll be in dy. And we'll work a couple of examples of each kind. But it's different. This is one of the coolest things to turn sideways, in my opinion. Well, I like it. Becca's a no. Okay. So on the closer look, there were a couple of things in the book that I wanted to pay special attention to. Here we have Rx or Ry is the radius of the disk. Okay, there's different kinds. But one thing you need to be able to do is you've got to know if it's perpendicular to the x-axis. If you see the words perpendicular to the x-axis, then you're going to be in dx. And you need your equation to be y equals x stuff. Perpendicular to the x-axis, that means that it's going to vary with x, dx. So you need your equation to be y equals x stuff.
I thought it was parallel. You said parallel.
If I'm parallel to the x-axis, then you want y. Can't we just pick one? So here's what it says up here. Another way to determine the variable of integration is to draw the radius of an arbitrary or circular cross-section. So let's say I have this function and it's operating perpendicular to the x-axis. Then I want my stuff in dx. Versus if I'm revolving my solid, let's say this is my function, and I'm perpendicular to the y-axis, then I want my information in dy, where I have x is equal to my equation in terms of y. Did I say it backwards a minute ago?
Yeah, we said parallel earlier.
Well,
I think we're talking about
yeah, the axis of rotation. Versus your cross sections.
I thought we were still talking about the axis of rotation.
I'm talking about the radius.
Okay, yeah.
Yeah, so if your radius is perpendicular to the x-axis, you're going to be in dx. If your radius is perpendicular to the y-axis, you're going to be in dy. So I think I was right both times, but talking about two separate things.
Yeah.
Okay, cool. In other words, Cohen was wrong. No, I'm just playing with you. I'm just playing with you. Good questions. Are we good here? Any questions about this? I mean, besides the fact that you have all the questions.
No, we're just trying to prove each other wrong. Let's apply it.
Let's apply it. Seth says let's just work one. Quit talking. Okay.
That's not what I
Got it.
I didn't say quit talking.
That's what he said.
No,
That's what he said. Basically, Seth said, let's do the thing.
that's not.
All right, so here's our example. It says, example 5. The region bounded by the graph of y equals square root x. So that's this picture right here. Can you see this? This is y equals square root x. And the x-axis, so that's important. That tells us pretty much what it's rotated about. If we weren't sure, then it follows with it's rotated about the x-axis. But a lot of times they'll give you that bottom boundary as your axis of rotation. Sometimes not, so you got to read carefully. We are bounded between 0 and 1, so between x equals 0 and x equals 1. And it's rotated about the x-axis, so if you can imagine, you've got this picture, of this thing, and then they turned it, and they started rotating it about that axis. So it looks like it cuts out maybe a big megaphone looking shape. Can you see it?
How do they make this stuff look 3D? It's impressive.
It is. I'm telling you, that's why I picked this textbook, because I thought these pictures beat all the other ones. All the other pictures that I kept seeing were two-dimensional. And in this situation, you need it 3D. So you can see what has happened here. You can see that your cross-sections are, or that your radius is perpendicular to the x-axis. Can you tell that? Which tells me I'm going to be in dx. Okay, so you kind of understand the picture. You kind of see what we're doing. Let's get an area here. We know area is pi r squared. But how is that r going to be computed? Yeah, it's the distance from the function to the x-axis, which is square root x. That's the y value. That's the height. So area is going to be pi times square root x squared. When I square root x, I get x. So area here is going to be pi x. So our volume on the interval from 0 to 1 is going to be pi times the integral of x dx. I'm just kind of writing on the same picture. Is that okay with you? I'm going to have that equal to pi times x squared over 2. Again, if I didn't do any calculus, I missed it. Right? You've got to integrate. Is equal to pi times 1 squared over 2 minus 0 squared over 2. Or pi over 2. There's your volume. So pi over 2, whatever's, liters, would fit into this volume if it was hollow. It's not hollow. Questions? Kind of understand? I much prefer these because they're always circles versus the cross-section business that are different shapes. That gets real hairy. So in my opinion, this process is much easier than that.
I just realized they shade their drawings. That's why they look so 3D. They shade them.
Oh, that's nice. It's gradient. Yeah. All right, so example 6, it says the region bounded by the graph of x cubed, y equals x cubed, y equals 1. So we've got a top, y equals 1, and x equals 0 is rotated about the line y equals 1. Find the volume. Okay, so now be careful here. Okay, we know our area is going to be pi r squared, but we need to have a conversation about r. When we're measuring r, we always want to measure high minus low. My high function minus my low function. Or if I'm in y, my left function or my right function minus my left function. Since we're in x still here, how do I know I'm in x? Because y equals 1 is parallel to the x-axis. That means I'm still in dx. Okay, so my volume, I will still be in dx. If that's the case, then my radius is found by doing high minus low. High minus low. Okay, so what's high here? This, y equals 1. That's high. And the bottom function is going to be y equals x squared. So the radius is going to be 1 minus, it's x cubed. 1 minus x cubed. That's my r value.
What about when it goes above the axis of rotation?
The radius is the same.
Oh, yeah, same number.
Wait, why is it 1 minus 1?
Because we always do high function minus low function to find the radius. And your high is y equals 1, and your low is y equals x cubed. So our radius there is 1 minus x cubed. I can't stand that one right there. Gotta fix it. So our area is going to be pi times, open parentheses, 1 minus x cubed squared. Okay. I think I'm going to start on a new page with volume. Volume is going to be from 0 to 1. And I'm going to pull that pi to the front. And I'm going to have 1 minus x cubed squared dx. Being so careful to not do what? Distribute the 2, right? Sad day. Instead, I think it's best if we go ahead and FOIL this out. 1 minus x cubed by 1 minus x cubed. That's going to give me 1 minus 2x cubed. Do y'all see that? I got a 1 and a negative x cubed and another negative x cubed, so I'm calling them negative 2x cubed. Huh? No u sub here because there's nothing that would cancel with the 2x or the 3x squared. And so then I'd have to get x in terms of u. That's a lot harder than if we just FOILed. Plus what? What's on the end? X to the 6th. So we got pi times the integral from 0 to 1 of 1 minus 2x cubed plus x to the 6th dx. Thomas, I tried that. His question was, could we not do u sub here and let u equal 1 minus x cubed and then integrate u squared? The problem with that is when I take du, I have a 3x squared and nothing to cancel with it. U sub would have been a really great option if this function had had an x squared in front. Does that make sense? So we're left with just the nasty. Okay, so antiderivative of 1, x minus 2x to the 4th over 4 plus x to the 7th over 7 on 0 to 1. This is nice, though, because the bottom limit's 0. At least it's not super gross. 1 minus 1 to the 4th over 2 plus 1 to the 7th minus 0. 1 over 7. I don't know what I'm thinking. One minus a half. When I get half. Half plus 1/7. 9/14. Right?
9/14. Yeah, you're right.
Y'all are counting, that's 2. I'm going to owe you a popsicle or something for being so mean to Cohen today.
I didn't even hear what you said.
I said if y'all are counting, that's 2. 2 for me. Hey, I got to take it when I get Cohen's smarter than I'll ever be. It's fine. But I can do 1/2 plus 1/7. So there's my feather for today.
This is gonna sound absolutely like crazy, but to me,
Should I pause?
I don't know, it smells like a car wash, and I don't know why.
It literally does not.
Yes, it does.
Do you mean soap?
I'm gonna eat soap.
Okay, here's our last problem. This is example 7. This is example 7. And here we're going to turn sideways. Okay? Literally. Things get a little sideways here. It says the region bounded by the graph of y equals x cubed, y equals 8, and x equals 0. Okay, so this should be your picture. We're going from y equals x cubed to y equals 8. Question, where's this intersection right here? What's this point, this ordered pair, where y equals x cubed and y equals 8 intersect? Ordered pair. 2, 2, 8. Good. Why? Because when x is 2 in this function right here, y is 8. That's how we got that intersection. Everybody good with that? Okay. We are intersecting x equals 0, so that's this vertical boundary line. Horizontal top lid boundary line is y equals 8. And the function is y equals x cubed. And so far, this feels like it could revolve around the x-axis and be exactly like what we've been doing. But it doesn't. In this problem, they say this is rotated about the y-axis. So now it's going this way. Okay, it's making like a vase. Something of that nature. Do you understand? So since we're going around the y-axis, we have dy, which means I need x equals. Can you walk through, because that's important. That's like the crux of solving these problems. Knowing which axis you're revolving around and knowing what format you need your equation in. So if my equation is x cubed, then I just want to solve for x. So I'm going to cube root both sides, and x is equal to the cubed root of y. And now I have my stuff in terms of y. Is that pretty solid for you guys? Get it solid? Ha! It's a revolving solid. Sorry. Nevertheless, our area is still a circle because we're rotating. We're still carving out circles here. Area is pi r squared. But now we have to have a conversation about r. R is the distance from the outer function to the y-axis. Outer function to the y-axis.
The x left or over there?
So right minus left. What's the outer function called? Cubed root of y. Cubed root of y. Because we turned everything into y. Okay, so this r is going to be the cubed root of y. You could put minus 0 if you just wanted to be in the habit of knowing I'm going to subtract whatever my inner function might be, or whatever that inner rotation line might be. But this r equals the cubed root of y is what's going into this area function. So we're going to have area is pi times cubed root of y squared.
We do y to the 2/3.
You could do y to the 2/3. I think I would like that better. Y to the 2/3. That's knowing that the cubed root of y is y to the 1/3, and when I square that, I get to the 2/3. Everybody solid with that? Okay. So there's my area function. Now we want to go into volume. So volume is going to be the integral from, and we're in y, so we're going to go from bottom to top, 0 to 8. From 0 to 8. Otherwise, we could have gone from 0 to 2 if we were going left to right. We've got a pi in front, and we had y to the 2/3 power as our function. Y'all got it? It's 5/3.
3/5 times
3/5 y to the 5/3. Good. On 0 to 8. We got pi times 3/5 of 8 to the 5/3. Would you rather raise 8 to the 5th power and then cube root it?
other way around.
Or cube root 8 and then raise it to the 5th power? What's the cube root of 8? 2? 2 to the 5th? 32. Good. Good. So we've got 32. I don't know. 32 times 3, 96. How about if we call it 96 pi over 5? That seems exact. Cool beans? Okay. Tomorrow we'll do what's called the washer method. So we'll finish this whole chapter with the washer method. This is enough to get started on your homework though. Cool? All right.